This video is about the conduction of the nerve impulse by the nerve fiber, and at the end of it, the student will be able to indicate the direction of propagation of the nerve message in a neuron, indicate the effect of the diameter of the fiber and the myelin sheath on the speed of conduction of the nerve message, and finally to list the characteristics of action potential in a nerve fiber. First, let's study the direction of the nerve message in a neuron. This is a non-myelinated neuron. This is the cell body, the nucleus, and the dendrites, and the yellow part of the neuron is the axon. Let's notice the direction of propagation of the nerve message. The red light represents the nerve message, and as you see, it propagates from the cell body in direction of axon terminals. One might ask why the nerve message propagates in only one direction. To find the answer, let's study the results of this experiment. We will apply two successive effective stimulations separated by different time intervals at the same point of an axon, and we will study the response of the nerve fiber. Let's see. The first time interval is 1 millisecond, and this is the response. 5 milliseconds, this is the response. 7 milliseconds, this is the response. 8 milliseconds, and finally 9 milliseconds. As we saw, for time intervals less than 8 milliseconds, the nerve fiber didn't trigger an action potential due to the second stimulation. What does this mean? This means that the region needs at least 8 milliseconds to be re-excitable or re-stimulated. What do we call this time interval? We call it the refractory period. What's the origin of refractory period? The effective stimulation triggers a depolarization and an inversion of polarity. Let's suppose that region X of the axon is the one undergoing depolarization and inversion of polarity. Depolarization is able to displace. So, when depolarization leaves region X to region Y, region X undergoes repolarization, then hyperpolarization before it returns to resting state. And during this time, the ionic concentrations are modified so that the region can't be depolarized before returning to resting state. This makes the depolarization move towards the region of the axon that are at rest. Now, this document shows the variation of the speed of conduction of the nerve message in myelinated and non-myelinated nerve fibers as a function of diameter of the fiber. What can we draw out from this document? We can draw out that the speed of conduction increases with the increase of the diameter of the fiber. And for the same diameter, the speed of conduction in the myelinated fiber is greater than that in the non-myelinated fiber. And what's the origin of this difference? Let's see. In this experiment, we have two nerve fibers of same diameter. The first one is non-myelinated and the second one is myelinated. And we know that the myelin sheath is a discontinuous layer. So, in the axon, there are regions that are uncovered by myelin, and these regions are called nodes of Ranvier. We will stimulate the two nerve fibers that are of same diameter with the same intensity of stimulation, and we will notice the speed of conduction. This is the speed in the non-myelinated fiber, and as you see, in the non-myelinated fiber, depolarization should pass by each point of the axon. But in the myelinated fiber, depolarization jumps from a node of Ranvier to another, and it doesn't pass by each point of the axon. What do we call this kind of conduction in the myelinated fiber? We call it the saltatory conduction. So the myelin sheath speeds up the conduction of the nerve message because it ensures a saltatory conduction. Depolarization only occurs at the level of nodes of Ranvier and not at each point of the axon. Finally, what are the characteristics of the action potential? First, the action potential doesn't appear unless the threshold intensity is reached. Second, the action potential is able to propagate along the axon. Third, starting from the threshold, the action potential has the same amplitude. And finally, the action potential keeps the same amplitude and the same speed no matter how much is the covered distance.